Alright, here we're going to look at work and energy of a rigid body. So again, we're going to take a rigid body, like we have here, and we're going to look at one particle, and then sum up what I know about all the particles to find what's going on with the total rigid body. So for this one little particle I, the kinetic energy is 1/2 VI squared times its mass, which is dm. So the total kinetic energy of this rigid body is the summation of all the little tiny dm's, 1/2 dm v of each little particle squared. Okay, so let's look at the velocity of each little particle. Okay, I can use our relative motion equation, which is Vp plus omega cross r. So Vp has an x and y component, omega cross r, where r is a distance from P to I. So I go x and y is the location. Okay, so when I do that, I get an equation that looks like this. I've got some stuff going in the I direction, some velocity in the j direction. Okay, now if I square that for this velocity, I actually am going to take vectors and I'm going to dot them together. I'm going to get a scalar value, which is what energy actually is as a scalar. So I basically take the I component squared plus the j component squared. When you do all the rigmarole for this, it breaks down into this sort of equation. This last piece comes from the fact that I'm going to get x squared omega squared plus y squared omega squared. Well, x squared plus y squared is actually r squared from Pythagorean theorem, so that's where that comes from. Okay. Therefore, I can plug this value for vi squared, that's the velocity of this particle, into my integral to find the kinetic energy for the entire rigid body. Okay, so distributing each one of these components in, basically taking them all times 1/2 the integral dm. Okay, I have an equation that looks similar to this. Now, the middle two terms, okay, if p coincides with g, that is, do all of this stuff for the center of gravity, okay, rather than some arbitrary point p, these middle two terms actually go to 0 because they're basically the definition of the centroid. So if I set the centroid equal to point P, those both go to 0 and go away, and all I'm left with is 1/2 mv squared of the center of gravity plus 1/2, and then this integral right here, r squared dm, is I. So my kinetic energy of my rigid body has two components. It has the kinetic energy, 1/2 mv squared, as well as rotational energy, 1/2 I omega squared. Now, energy is a scalar, so I can just add those together. Okay, they don't have directions. It's not like one's a rotation, one's a translation, right? It's total energy. Energy is both translation and rotation added together. Okay. Now, I can do this about a fixed axis. When I do that, the velocity to the center of gravity is basically its angular velocity times the distance from the point to the center of gravity. Okay, plugging that into my kinetic energy equation and manipulating things around, recognizing that this term within the parentheses is the moment of inertia about the point of pure rotation. I can reduce the kinetic energy simply to 1/2 I O omega squared, where O is a point of pure rotation. Okay, and that's going to include both the translation and the rotation part. So you can take the total kinetic energy to be this if it's about a fixed axis, or this other equation works for anything. Okay, you know, based on the center of gravity. All right. One more thing we need to talk about before we get into the equation for work and energy, and that's the work of a couple. Okay, we've already dealt with work of different forces. So if I've got a couple on a rigid body like this, well, what that basically is it's actually two forces at some distance r apart from one another. Okay, so if I think about the rotation that that's creating, or the displacement, okay, basically I have r over 2 times d theta, and that gives me my little displacement ds in each one of these. Okay, so I can write the work of that couple moment as just each of the forces times each of their displacements, as shown here, and they're going in the same direction. Okay, where the displacement is just the arc length r over 2 times d theta, shown here and here. Adding those together, I just get fr d theta. Well, f times r, by definition, is what the couple moment equals, so I get md theta. Therefore, the work of a couple is the integral of md theta, okay, which is just the moment times the angular displacement. Okay, and this work is going to be positive if the moment is in the same direction as rotation. If moment is opposite rotation, then that would be negative work being done. Okay, for the common occurrence where I have a constant couple, well, I just take the moment, bring it outside the integral, and gets basically the moment times the change in angular position, as shown there. Okay. Quick word, if I have a rolling body, recognize that friction does not do any work, and that's because at the point of contact there's no velocity, right? It's not moving at the point that the force is actually acting. Therefore, it does no work. So if you've got a rolling body, just recognize that there might be things doing work, but friction, if it's rolling without slipping, is not doing work. Friction may be doing work if it's slipping, but not if it's rolling without slipping. Okay. That leads us to an equation that you've seen before. This is the kinetic energy equals the initial kinetic energy plus the work equals the final kinetic energy. Okay, this is the exact same equation. It's a scalar equation. The one difference is my kinetic energy now has both translation and rotation, and I've added one extra work that might show up, but it is the same equation. Okay, just recognizing that I need to include the rotational energy in with the total kinetic energy initial and final. As shown here. But it's the same equation, it's a scalar equation, and that's what you apply, just remembering that rotation.